So last week we just finished the term 2 for year 4 student for preparation of the opportunity class, and they're gonna have another 2 weeks to have the OC test in 27th of July. And today I just want to collect some of the questions which is asked by some student, and I'm gonna categorize them into 3 different sections. We're gonna focus on some very basic thinking skill abilities that are very likely to be tested in the opportunity class. Today we're gonna start from the first one, which is called systematically counting. Systematically counting actually is very widely being tested in selective test in the OC test, combined with for example, like a chance, combined with geometry. So this is a very basic concept. Regarding to the systematically counting, our purpose for systematic counting is that we have to make sure, firstly, we are not missing any countings there. And secondly, we have to make sure we will not double counting anything. So that is why we're talking about the systematically counting, which is we have to systematically follow some procedures to counting to make sure we will not missing anything, we will not double counting anything. So, for example, look at this question. Pao take one counter out of each jar without looking and add them together. How many different sums are possibly? So, basically, this question asking us, if you take one counters from each of the jar, how many different sums we can have? How can we make sure that we can systematically counting all the possible sums that we could get? So very frankly speaking, so when we try to counting them systematically, so we can see that there is 6 counters in the first one and 3 counters in the second one, right? In the second jar. So if we want to count them in the systematic way, what we can think very reasonably is from jar 1, for example, if we take this jar 1, this jar 2, from jar 1, right? When you take it out, how many different counters you can take it out? When we look at each of them, we will see we have 1, 2, 3, 4 different possibilities. So we're gonna list it is 1, 2, 3, and 4. That is 4 possible counters that we can take out from jar 1. So for each of the counters that you take out from jar 1, for jar 2, how many possible counters we can take? It's 3. So we follow them by 1, 2, 3. So then that's how our systematic counting is. If we take the number 1, the number 1 counters from the jar 1, so we get the 3 different combinations from jar 2. So the different sums we can get is 1, 2, and 3. And then we just repeat the procedures to say if the counters we take out from jar 1 is 2, then we have another 1, 2, 3 to combine with. Then we have different sum which is 2, 3, and 4. Then we repeat these procedures until we get the final one, which when the first one you take out is 4, we still get 1, 2, 3. Then the sum will be 4, 5, and 6. Right? So then we get that is the very secure way we can including that we will not miss any countings and we will not double counting anything. So basically the different result we can see is 1, 2, 3, 4, 5, 6. So the total different sums we could get is 6. That is how we do this in the systematic way. Yeah, that is called systematic counting. That systematic counting is very essential abilities that we need to have in the thinking skill. Look at that's question number 2. This is another very typical question about systematic counting. When we counting about how many different traveling ways from L to N, so what systematically counting we can have in here? Yes, we just follow by each of the nodes to see how many different ways we can go in from there, and then we just make them in the tree diagram to try to make list of all the possible ways that we can travel from L to N. For example, if we start from L, how many different options we can have? Apparently, we got 2 different ways, right? Let's name it 1 and 2, which means if we going out from L, we got 2 different options, which one is 1 and another way is 2. Now, let's focus on 1 only. So when we go into 1, and then following by next one is we got another 2 possible different routes that we can choose. So let them put into another 1 and 2. So then after that way, we can follow as 1, we go to another 1 and 2. After that, we are reaching to the same knots. And then from these knots to M, we only got a 1 way. And then from M to N, we got another 2 ways, which means, let's say it's another 1 and 2. So, which means from this one, we can go to another 1 and 2. And then from second route here, we also got 1 and 2. Right? Basically, that is all possible ways that if we want to go from L to N via the first choices here, right? The route number 1. Then the same procedure, we just counting that if we go from L to the second one, what's the options we can have? From L to the second route, the first leg we can see we got another 2 ways to go, which means we name it 1 and 2 as well. So from 2 out, we got 2 ways to go, which is 1 and 2. Then we're reaching to M. To M, then we facing the same scenario. Is we want to go, we coming out from 1, we have another 2 options, 1, 2, and we got another options from 2 is also 1, 2. So in this tree diagram, we can list all the possibilities that we can have in here to make sure we are not double counting anything, we didn't miss anything counting. So the different routes we can have, if I'm putting the different colors here, it's more easy to read. So this is 1, this is 2, this is 3, and this is 4. So from the knot number 1, we got 4 different routes. From knot number 2, we got another 4 different routes. So totally, the routes we have is 8. So this is another example showing us how to do the systematic counting. And look at this question. Question number 3. So for this one, if we are doing the systematic counting, like how many small cubes that we need to complete the surrounding these 3D shapes with 1 layers outside. So if we want to counting this way, mostly the student might think is, okay, if I'm adding 1 layers out, and we'll be thinking about is like on the top, how many squares I gonna have more? On the bottom, how many blocks I need to adding? And then on the right side, on the left side, how many I need? And on the right side, how many blocks I need? Of course, we can counting in that way, but here it seems like a little bit complicated because the number of the blocks on the top and the bottom will be same, but on the left and the right might be different from the numbers of blocks from top and the bottom. So this is kind of a little bit hard to count them separately. Under these circumstances, there's another system counting is, can we just think about the end, how many blocks there, and then to look at the beginning. This is called beginning to the end. Then we do the subtraction to find out how many numbers of the blocks we need to laying out for the outer layer of the whole cubes. So if we think about this way, let's think about it. For the end, if we want to put one layers outside this 2x2, yes, this is 2x2 blocks. So if we want to put one layers outside, what's this cube's gonna look like? Just think about it. As end, if we put one layers outside each of the faces, then for each of the faces, we're gonna have is a four numbers of blocks, right? With another 4 number of blocks, and the height is also 4 number of blocks. So in this scenario, we will totally get 64 blocks after we put one layers outside of all faces. And at the beginning, how many blocks there? That's going to be very easy to count, right? That is one layer is 4. I got 2 layers, which is 8. So at the beginning, I only got 8 blocks there. And at the end, when I put one layers outside of the all faces, I got 64. So how many we're going to add in on? So 64 minus 8, that is 56. So this is another very efficient systematic counting ways that we can quickly get the answer. So if this is the scenario, let's look at back this question. Just now we are doing the systematically counting, right? But just to get inspiration from the questions, question number 4, can we have the better strategy for this question? I might just give you a little bit of time to think about it here. Do we have the better strategy for this one? Since we're talking about the sum, do we have another ways to calculate, like what's the boundaries for the sum? What is the minimum one the sum could be? What is the maximum one the sum could be? And then we can find the how many different sums we could possibly get. Yes, some students might think about already. They were told me to say, Rex, look, from jar 1, right? From jar 1, the minimum numbers I can take is 1. From jar 2, the minimum numbers I can take is 0. So which means minimally their sum will be 1. And maximally from jar 1, what I can take is 4. And from maximally from jar 2, I can take is 2. So which means the maximally the sum is 6. Now, when we look at the jar 1 and jar 2, so the increment of each of the counter is only by 1, which means our sum could be covered from all the numbers from 1 to 6. Okay, so the different sums from 1 to 6 will be 6 in total, which means it could be 1, could be 2, could be 3, and all the way it could be up to 6. So this is another very efficient way. We'll look at what has beginning and what is it at the end, and quickly to get the answer. Okay, through some of these questions, we just show you like that is the efficiency about how do we count to make sure that we will not missing anything, we will not double counting anything. So this question, I'm leaving here as your homework. So if you want to work out the answer correctly, you need to counting the edges of these houses by systematic way to know how long that we need the timbers to get the total length of the timbers. Then you will find the answer. Okay, so if you got these answers, you can choose it, and then later on you can just find me and check if your answer is correct or not. Okay, thank you guys. We're just staying here, and tomorrow we will continue to find out another topics which is going to be important in the opportunity class test. Thank you for today.